we can invite our next speaker, Fabiano Santos. Ah, okay, great.
Okay, thank you, everyone.
Thank you,
Hi.
Salman, again.
Hi, Byron. I'm here.
Hi. Okay, we can start. Thank you.
Okay. I can share my screen.
I think so, yeah.
Okay. Okay, can you see my screen?
Yes, perfect.
Okay. Okay. Thanks, Byron, by the presentation. Thanks, Byron, by the invitation for participate of the conference again. This conference is a good moment for us to show our ideas and the recent work and progress of the holographics and applications in physics. This talk, I will try to show some of my results that I produced in recent years using the application of the Horndeski gravity combining with the AdS BCFT correspondence, right? Okay. This is the summary of my presentation. I am perform a small introduction about the BCFT correspondence and discuss some applications. And with this, I talking about the BCFT correspondence and why this new extension is good to describe some problems that appears in the description of the strongly coupled system using the AdS-CFT correspondence, right? And with this, I am talking about the holographic transport coefficient for the quark-gluon plasma, right? And another way to study these things is using the fluid gravity correspondence for try to see what happened with the quark-gluon. And I finish with the conclusion and discussions. Okay, as you know today, the AdS BCFT correspondence started with the work of Maldacena and Witten in 1997 and 98. And after this proposal, in the last 3 decades, the people applying this model, right, in some systems, as you know. But the idea behind of this duality is perform a description of gravity in 4 dimension, for example, in 4 dimension using the conformal field theory, right? The conformal field theory is a theory that are invariant under a scalar transformation for the boundary side, as you know, okay? But in the first moment, this model is a theoretical and mathematician model, right? And since this proposal, from the overview point of a theoretical model, many people try to apply this in systems like the condensate mirror, right? Where the motivation to applying this in the condensate mirror systems is due to the fact that the quantum critical points have a scale, and a space-time scale invariance, right? This is a motivation. But a remarkable result of the application of the AdS-CFT correspondence is in the description of the quark-gluon plasma, right? This description can be done using an action gravity, like the action gravity, plus an action with the scalar field, right? Where with these ingredients is possible, we perform a mimic with the KCD-like models, for example. And with this, we can realize a description where it's possible see what happened, for example, in the quark-gluon plasma. And the important coefficients for these descriptions is the shear viscosity and bulk viscosity. Recent works, the people apply this connection and this mimic. And it's very interesting because we have a conformal fluid, right? But this conformal fluid implies that the energy momentum tensor is zero, and this is implied that the bulk viscosity is zero, right? But we have a little, how can I say, I think that it's not correct to say a little problem, but we have a little disagreement because from the overview point of the experimentalist, this fluid or plasma have a low viscosity, right? And this viscosity, low viscosity, indicate that we have a liquid but not a gas, right? And my idea with my collaborators during recent years is extending this theory. For example, extending the gravity and extending the AdS CFT. And what happened with these things if we extending the theory? This is the idea, and a motivation is the fact that the bulk viscosity is zero in Einstein gravity. But if we consider another theory of gravity, what happened with these things? There is the motivation, right? This is the motivation here, right? We change the gravity side and we change the boundary side. And with this, we can see what happened with the transport coefficients, like the shear viscosity and bulk viscosity. Okay. Okay. For this, I consider the new extension of the AdS CFT known as AdS BCFT, right? This B is a boundary. And this proposal was performed by Takai in 2011, right? Where the idea is that we have the Einstein gravity and we have a boundary term. And this boundary term is described by this action. Of course, here we have a duality between a gravity in 3 dimensions and what is described by a theory in 4 dimensions, a boundary conformal field theory. An interesting model that I considered with my collaborator was the special truncation of the Horndeski gravity. This special truncation, the people know as the John sector of the Horndeski gravity, right? Okay. The idea is construct a boundary term for the Horndeski gravity, right? Because if you see here, for the Einstein gravity, this is the boundary term, right? But for a new, not a new, right? Because this theory is created in last 5 decades, right? But is the idea that I say new is new for the AdS BCFT correspondence, right? If we consider a modified gravity theory like this, how is the form of the boundary profile, right? This is the form of the boundary profile for the Horndeski gravity, right? And here, of course, we have Horndeski Lagrangian density, of course, and we have the Maxwell field with the other things, right? Or with this other tensor, because we include this because we try to see what happens when we apply a external magnetic field, right, in this plasma. Okay, with this, we need of the more 2 ingredients. This ingredient is a black hole in 5 dimensions, and in the gravity side, and for the boundary side, we have an induced method in 4 dimensions, right? Because we establish AdS 5, BCFT 4 correspondence, right? And for the gravity side, this is the solution, right? Where alpha and gamma are Horndeski parameters that come from for the density Lagrangian, okay? And in the boundary side, we have this induced method, right? And this induced method have a solution like this, like the equation 4, which have the contribution of Horndeski gravity, right? If the contribution of the Horndeski gravity is 0, we recover the usual case of the tachyonage in 4 dimensions, right? Okay, but the equation 4 is very interesting for us because we have 2 possibilities here. We have a possibility to solve this equation numerically because the solution, the total solution is numerical, or we can do realize an extension in this, considering the Horndeski coupling parameter very small, and we study these 2 behaviors, right? But in the left side, we have the numerical solution. And the right side, we have the approximate solution. What is the idea to describe these 2 solutions? The idea is because we are interested in compute the thermodynamic quantities, like the black hole entropy. And if you consider the numerical solution, the total solution is very complicated to solve, right? Using the holographic scheme. And when I put the behavior of the approximate solution, we have that the solutions are similar. And of course, is more better we working on with the approximate solution, right? Because we can to obtain analytical expression for the transport coefficients, right? Okay. To apply the AdS BCFT correspondence, we need to compute the area of this figure, right? When you compute the area of this figure, we found the black hole entropy, right? Of course, the equation 6 is an approximation solution for our case, right? And this expression is very interesting because we have no trivial terms, right? But if you see here, we have a possibility to relate these terms, the horizon, with the temperature of the black hole. And when we replace the temperature here, 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 and here, and we consider the low temperature case, this term is 0, 0, 0, 0. But we have a term that is not 0, right? But calm down while I'm explaining what happened with this term. And if we consider a higher temperature phase, of course, infinite temperature, these terms, how can I say to you, is irrelevant for the description, right? But in the low temperature, we have a boundary entropy for the, of course, here these terms are corrected by the Horndeski gravity, right? And in the low temperature, we have residual information for the black hole. What it means this? This means that the black hole continues emitting information, right? Same in 0 temperature. And recently, the professor Sunskine performed many works where proposed another idea for this. The idea is that, for example, the classical entropy for the usual gravity, for the Einstein gravity, is 0 when the black hole reaches the thermal equilibrium, right? But from the overview point of the quantum complexity, the black hole continues emit information because these guys are interested in solve the problem of the lost information paradox for the black holes. Right? That is the idea. And when I see this work, I think that the extension of the AdS BCFT with the modified gravity model can be a direction to sound or to see these things, right? But this is my opinion and my result. I don't know that I am sure about this, right? But in some sense, this result is a good prediction, right? Uh, sorry, for we see these things, right? In summary. Okay, but back for the black hole entropy, as I know in the beginning of the presentation, the idea is to study what happened with the book viscosity and shear viscosity for the modified gravity theories for Horndeski gravity, right? And for that reason, we need to compute the relation between the book viscosity and the entropy, shear viscosity and the entropy, right? And of course, we need to include the effect of the magnetic field. We did this using the Dirichlet boundary condition, right? When we perform this, it's possible we rewrite the boundary entropy in terms of the magnetic field. Okay, and using the tensor perturbation, it's possible we extract the holographic transport coefficients, like the shear viscosity and book viscosity. Okay, and what happened now for the large temperature and the low temperature with these transport coefficients? That is the idea. Okay, when we increasing the temperature, we see that, in fact, these two transport coefficients go into zero, right? But when we decrease the temperature, we see this behavior here. And this behavior here is doing this thing, right? And of course, our model, we perform an approximation, right, to describe this. But this approximation, in some sense, is very interesting for describe the small viscosity as the people think that is necessary here. And if you see, for example, if you remove the boundary term and the Horndeski gravity, this limit is saturated, right? We recover the all descriptions that are predicted by the Einstein gravity, right? This is need to happen. And the professor Gutse performed a description about this model, right? But this description was performed by numerical computation because it's not possible to solve in an analytical way these things. But when we take these two transport coefficients and relating both, we found this equation, right? And this equation is very interesting because if you see here, for example, if we choosing this value, which means the general sense in the model, we recover the all results, usual results. What does mean this? This means that we have no contribution of the scalar field. Because if you see in the Horndeski action, Lagrangian, we have that the couplings alpha and gamma are related with the scalar field, right? And if we remove them, we back to the usual results in Einstein gravity, of course, where the both viscosity are zero and the energy momentum tensor are zero. But when you compute the energy momentum tensor, right, we found this behavior, okay? Which means that the energy momentum tensor is not zero more, right? Here in this description, in this model, of course. Of course that I am working with the Horndeski gravity, right? But I don't see what happened for the other theories beyond Einstein, for example. But for example, for the density theories, when I compute the shear viscosity, this viscosity are not saturated for the usual case because we have the other contributions, right? But I am not studying the quark-gluon plasma in density theory, for example, right? Okay, and we see that the spirit of sound have a no trivial value, right? Because this trivial value here is only for the conformal fluid, and for the conformal fluid plasma, the plasma, happen when the Horndeski couplings are zero or are very, 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 very small, right? Because when we increase in the force of these parameters, we have no trivial values for the transport coefficients. Okay, another way for you check if our results are in fact have a good agreement with the other two ways to describe the quark-gluon plasma is through the fluid gravity correspondence, right? When we analyze the anisotropic pressures. Of course, we have a broken of the conformal symmetry, right, with the Horndeski couplings and with the boundary term, of course. But when we go to the ultraviolet regime, we have we recover conformal behavior, and this result is expected by the usual gravity theories, right? Which means that the energy momentum tensor is zero. How minutes I have, Byron? Okay. If I try to see the behavior of the pressures, I have a good agreement with the QCD, right? With the QCD lattice. Of course, we are performing a mimic. Remember, we are coupling a gravity model with the scalar field to perform a mimic, to perform an alternative description of the QCD, because as you know, it's impossible for us treat the QCD in a perturbative way, right? It's not possible for us. We realize on a perturbative theory to describe these phenomena. And the strong contribution of the AdS CFT for the AdS QCD is the fact that we can to describe this model, but not perturbatively, right? In some sense. Okay. 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 I summarize my results. Okay. In your discussions with my collaborators, we see that in fact our model agrees with the QCD lattice, right? Because this mimic with the scalar field, remember that the perturbations are in the boundary, not in the completely theory, for example, right? No, are not in the scalar field, are not in the Horndeski gravity, the perturbation, right? The not the perturbation, but the approximation. The approximation are in the boundary, right? In the boundary tape profile. Okay, and okay, in fact, we have a good description for this transport coefficient. and in low temperature, we have a more strong contribution of the Horndeski parameters, right? And when we increase the force of the parameters. Okay, this is the reference. And here I would like to thank the Journal of Holographic Applications, my research group, my collaborators, and especially Bernard is my collaborator during the recent years, and the universities to organize the conference. Thanks a lot.
Fabiano, thank you for the nice talk. We can take some questions.
I'm sorry, you say?
Thank you for the nice talk, and I said we can take some questions now.
Okay.
Are there questions? No? Okay, thank you again, and Behnam, thank you for the organization. If you want to say something, please go ahead.
Thank you, Bayram. Thank you, Fabiano, and also thanks Salman for his great help to organize this conference. Please do not miss tomorrow talks. We have a special talk by Professor Kraus, and see you tomorrow afternoon.
Sorry, there is one question that I...
Yes, it's a question about how can you compute the thermoconductivity in this context. I not compute the thermoconductivity, right, for this context, but have a guy that worked on with the Professor Chris Pope that performed these things, right? If you want, I can send to you the paper. But in fact, I not compute this in this new context, right? But okay, it's a possibility that did in the future. But thanks for the question. But it's not difficult, Professor Mehis Sadehi. Okay, Mehis Sadehi. Okay. I know you through the papers, but not in person. Yes, it is. It's possible to compute this, right? It's necessary to perform some some new things, right, to compute, but it's not impossible. Maybe the thermoconductivity have the contribution, because I see some papers that the people compute this, but the relation depends of for example, the Gauss-Bonnet parameters. But here, I think that happened the same thing. And probably we have the contribution of the boundary, right? Because this boundary modifies the black hole entropy and consequently modify the all transport coefficients that we try to extract.
Okay, thank you very much.
One of those things, sorry, this morning in talk of Dr. Sudhakar Upadhyay, Fabiano asked a question, but he had a connection problem, but he is here now and can answer you, Fabiano.
Yeah, so that is a very good question. I think probably this could be applied, but I don't know the fate. Actually, I have not on that actually about the work. So it would be nice suggestion, I think, what will be the future we can discuss, I think.
Okay. Okay, thanks a lot. Because the presentation was very fast, and when I tried to ask you, the time stopped. But okay.
Yeah, that is a
Thanks a lot
direction
for
we
the
can
answer.
think of. Yeah. Thank you.
Okay. Thank you.
Bye.
Okay, thanks again,
Bye. See you tomorrow.
guys, by the invitation. Thanks, Bernard. See
Thank you,
you
Fabiano.
on Monday.
Take care. Bye.
for everyone.
Tomorrow afternoon we have next session.